in this problem, we're trying to make a symmetric matrix using some tiles. And a tile in this context is a 2 by 2 block, and each block has a number. So what does it mean for a matrix to be symmetric? So all that means is, if we look at the case of a 3 by 3 matrix, so let's go here. It just so it'll be 1 2 1 2. So it just means this number is the same as this number, this number is the same as this number, this number is the same as this number, and these numbers don't really matter. So if you draw some kind of line here, this section is symmetrical to this section. So that's all it means. And now a tile in this case would just be something of this sort, 2 by 2 grid, right? So the key thing is we had to focus on this main diagonal, right? And so what type of tiles can we put on this? Well, actually, wait, let me just first explain what a tile is in a bit more detail. So a tile is this 2 by 2 shape, and we're given types of tiles, right? So if we're given, so let's look at the very first test case, which is this, right? So we're given 3 tiles, and we want to make a 4 by 4 symmetric matrix, and each tile is a type, so we can use this tile as many times as we want. And the tiles are 1 2 5 6, so 1 2 5 6, 5 7 7 4, and 8 9 9 8. And then we want to fill a 4 by 4 grid to make it symmetric, and this is the answer that they give. Right, so if you draw a imaginary line across this diagonal, we can see it's 7 7 8 8 9 9 9 9 8 8 7 7, right? So this is symmetric. So the first thing to notice is that if m is odd, then there cannot exist a symmetric matrix made out by 2 by 2 tiles, right? Because if n is 3 here, there's a 2 by 2 here, and then we can't put any tiles here, 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 right? Because it's 2 by 2, so this will go out of the grid, this will go out of the grid, and we can't do that. But if it's, I don't know, 4 by 4, so that we add an extra row, add an extra column. Here we can just do 2 by 2 here, 2 by 2 here, 2 by 2 here, and 2 by 2 here. So yeah, we first care that m is even, and if m is even, then we know that we can make a matrix that is symmetric, right? So now we just have to check if there exist tiles that work, and when does a tile work? So if we look here, if on this main diagonal, we don't care about the top left and the bottom right values. We only care that the top right and the bottom left values, these two values, are the same, right? Because if we draw the main diagonal, we just care that these two values are equal. And if we find a tile like that, then we can find a tile to put across the main diagonal. And let's say we use this tile again here, right? Be 5 4 7 7. Then if this was 5 4 7 7, we don't really care what this and this is. This would be the same here, this would be the same here. So therefore, as long as we find a tile that fits on the main on the main diagonal, which means that this value is the same as this value, so I'll just call this A, B, C, D. As long as we find a tile where B equals C, we can make a matrix that's symmetric as long as m is even. So that's it. Okay, so we're given, are we given test cases? Yeah, we are. Okay, so in t while t minus minus. Okay, now for each of these test cases, we're given n and m. So we have n tiles, right? So then for n, let's just int a, b, c and a, whoops, b, c, d. And again, that's a, that's b, that's c, and that's d for every tile. So now that we have a, b, c, and d, we just have to check if there exists some tile where b equals c. So let's have some like Boolean variable called can, and let's set that as false, right? Whoops. So now let's can equals or equals, whoops, or equals b equals c. So what this does is if b ever equals c in any of the tiles we see, it makes can to true, right? And if can is true, then we know that we can do it, right? So if can is true and m is even, whoops, wrong one, and m is even, then we can just output, whoops, what is that? Yes. Otherwise we just output no. And I think that should be good. Copy this, paste this, and yes, no, yes, no, yes, 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 no, yes, no, yes, yes. Okay, submit. And voila.